Hello again. So I have the privilege to introduce our keynote speaker, Jonathan Overpeck. He's going to be presenting the impact of climate change and the challenges we face. Professor Jonathan Overpeck is an interdisciplinary climate scientist at the William B. Stapp Collegiate Professor of Environmental Education and the Samuel A. Graham Dean of the School of Environment and Sustainability at the University of Michigan. He has written over 200 published works on climate and the environmental sciences, served as a working group one coordinating lead author for the Nobel Prize winning IPCC fourth assessment in 2007, and also as a working group lead author for the IPCC fifth assessment in 2014. Overpeck recently served on the University of Michigan's President's Commission on Carbon Neutrality, and he currently serves on the State of Michigan Governor's Council on Climate Solutions, as well as the City of Ann Arbor. A round of applause to
Yeah, I've been hearing in the news, I might not be tweeting at X anymore, right? But you know, it's been a really hard decision to stay on that thing, that platform. Most of the journalism community is on, the media community is on X. That sparked a whole bunch of debate in the scientific community and alarm and perhaps more in the world at large. And so I want to talk about that and see if I can sort of help sort out what's really going on with climate change. But I'll tell you, those who don't want to listen to the talk very carefully, the bottom line is what you're doing is fantastic. You know, being on the governor's Climate Solution Council and working out that plan with Lisa Clark and all the other members, I never thought so much of it could get into legislation so fast after we produced that plan. And I didn't do squat, you know. I just helped be on the council and figure out what we have to do and provide motivation perhaps. And that's what I want to give you, is more motivation to keep at it, because you're doing a phenomenal job. And I'm a big believer in renewable energy, even bigger believer in the big thing in the COP right now in Dubai. It all comes down to whether they can come up with an agreement to phase out fossil fuels. Phase out fossil fuels. So in Michigan, our goal is we have to obviously get rid of the coal-fired plants, which I now think are on their way out, and everyone gets it. But we also have to get rid of gas. And I get the sense that you all feel the same way. All right. So is climate change getting worse, and is it too late to save the day? You probably know the answer, but I'll give it to you at the end just in case. We're living through something pretty remarkable, and maybe as being a climate scientist over the last 40 years, scary thought, you know, it's been incredible. I had a professor, you know, a colleague named Wally Broker used to say, oh, great natural experiment. You know, he was one of the guy who coined the phrase global warming. I mean, he was pretty pissed off at the whole thing that we're doing to the planet, but it's just amazing. These things keep happening and they're surprises. So what's the big surprise this year? Well, the global temperatures, air surface temperature. And unfortunately in this talk, you're gonna have to keep track of some, it's gonna be a climate science talk. All right. So you're gonna have to keep track of, there's the air, and there's the surface of the ocean, and there's the ocean more generally. I'm gonna talk about all of those. Okay, but air surface temperature means where we live, basically, around the planet. Humans live, you know, at the surface in that air. And it's off, the temperature increase is off the charts. In other words, we're gonna break a record, but we're gonna break a record by more than we've ever broken. And this last summer was the hottest summer ever by far. And up to now, we're starting to realize that this year is going to be off the charts. And we might even hit 1.5 degrees C for an annual temperature for the globe this year. Okay, we knew this was going to come faster than, you know, part of the problem with science is we're conservative, but a lot of us knew it was going to come faster than we thought. And this is where Jim Hansen has just been a visionary. Okay, we're not just talking about temperature though, We're also talking about all the climate extremes we're getting. And each year, we're getting more and more a taste of what is going to become the norm around the planet. And another big thing that's going on in the Conference of Parties, or COP in Dubai, is trying to get money behind loss of damage, which at the last COP, they passed with no money. And there's still not much money, but there's some. But the idea is that the rich countries are doing all the polluting, the poor countries are having to suffer for it, and that the rich countries should be paying to help the poor people in the poor countries make up for the damages, loss of life, and huge economic costs that they're paying. So you all know that there have been amazing heat waves. Probably the biggest one so far is actually in Europe, 2003. 70,000 people died prematurely. Amazing. And we've had just a host of things this year. Well, last year was Pakistan. This year it's Libya, 20,000 people died in extreme floods. Of course, these hurricanes that we're getting in the Gulf Coast are causing way more damage than before. The mega drought out west, I lived out west for a long time in Arizona and Colorado. They're running out of water and they're pumping the groundwater dry. What the hell are they gonna do when they're out of ground? You know, they're gonna have to learn how to live with less water, that's all. But that's not something they wanna do. And they wanna just burn fossil fuels and make the situation worse. But in any case, we're seeing real time, like every month, a new disaster around the planet. Right now, the Southern Hemisphere is going into their summer. So you're gonna start to see, for example, in Australia, some really hot, dry, fire-prone conditions, which could be like the last time we had an El Nino. And they had what they called a black summer, I think. It's unprecedented wildfire. Just like we had unprecedented wildfire this summer in the boreal forest up in Canada, and we all had to breathe that toxic smoke. Okay, in Michigan, we get a little of everything, but we're relatively well off in Michigan. But that's not a reason to keep your foot off, or take your foot off the accelerator. Because if we don't solve this problem, Michigan's gonna hurt too. And I'm not giving that talk today. A lot of you might have heard it already. But you know, for sure, we're getting a problem with our hydrologic cycle. And the important thing to realize about the hydrologic cycle, meaning rain, but meaning the extremes, drought and flood, are the two extremes of hydrologic cycle. Those extremes are getting bigger and more frequent and longer than before, because the atmosphere is warming and can hold more moisture. Very simple physics. You warm the atmosphere, it's going to get worse. And we know with perfect confidence in the scientific community, as long as we keep putting up fossil fuels, carbon dioxide and other greenhouse gases, meaning as long as we burn fossil fuels, the planet will get warmer. So we know with really near perfect confidence that these problems in the hydrologic cycle, driven by the temperature increases, will also get worse, okay? And of course, we all know that there's been more intense precipitation and flooding in Michigan. What you don't know, the other talk, is that there will come a time when Michigan will dry out as well. We're aridifying the planet, and depending on how bad we let climate change get, there will be more pretty dry summers in Michigan. Okay. Something to note for those who want to follow up and learn more about what's going on now is that the US climate assessment is produced every several years at the behest of Congress, and it's been doing that for quite a long time. The fifth one just came out. And if you go onto the web, and you can get a copy of it, and it gives you details of what's going on around the globe, not like the IPCC, which is like, phone book thickness, but in a much more summary fashion, and what it means for the various regions of the United States. These regions are colored on this map. And what we're looking at is the percent of increase in the percent of rain falling in the heaviest 1% of events, rainstorms. So in other words, we've had a 45% increase in the heaviest rain in Michigan just over the last couple decades. Okay? Good thing we don't live in New England, but of course, New England, what was their big news this year?
Wow.
Major flooding, yeah, right. So this is, everyone's starting to realize, Americans are starting to realize, and Americans, when you poll Americans, it's over 70% now, Americans feel climate change is real, it's affecting them or will affect them, and government and corporations need to do something about it. I'm not kidding you, best scientific polling says 70%. But it's our politicians who are getting money, say, from fossil fuel or the utilities, that are keeping the change from happening in our energy strategy that we need to curb this mess that we're creating. Okay, I have to always show this because this is a wonderful quote.
Not gonna happen.
It's not gonna happen. University of Michigan is having a workshop next week with all of the states and province leaders in the international Great Lake Compact region to come together, and we are telling them, you can't just sort of sit back and say the Great Lakes Compact is good enough. It isn't. I come from the Colorado River Compact, Rio Grande Compact. These things are laws that change through time, and who does the change? People. So we have to get more rigorous in our strategies to ensure a strong Great Lakes for the Great Lakes region. So we're working on that. But this is what John suggested I talk about. He didn't know I was gonna talk about that here, but what the heck, I had to do it somewhere. And the godfather of climate science is the guy who hired me out of grad school. So Jim Hansen is someone I've known for 40 years, since 1987. 1988 is when he went before Congress for the first time to say global warming has happened. I mean, no other scientist who had the cojones to do that. And he did it. Guy from Iowa. I was born in Iowa too, so I always like to point that out. But I grew up in Michigan. All right? He said, it is worse than we think. And I think he's right, and I want to show you why. Okay? And he said we would be darn fools and bad scientists if we didn't expect an acceleration of global warming. Well, scientists aren't darn fools, bad and always bad, but I'll tell you what they like to do. They like to debate things. You know, so he set up a minor firestorm of one climate scientist, say like Mike Mann, who I have incredible respect for. You know, he's written all those books, but I've written papers with him on things. He's brilliant. He's saying that isn't accelerating. And other scientists saying, like this guy, Zeke, House Father, saying it is accelerating. Okay, everyone has a different data set for global surface air temperatures. We're still talking about air here. But here's what Zeke put in an opinion piece in the New York Times. And he did an opinion piece. It'll be in probably a scientific paper before long. But the point is he wanted to make the point right in the middle of the debate so that the policymakers in this country would see what's really at stake. And every scientist agrees there is a big acceleration where you go from the gray to the colors in the rate of global warming. That's what we're looking at here, surface air temperature, global warming. This is using the Berkeley surface air temperature data set. That other pretty good university out of California. And you can all see that in around the 1970 mark, things really started to ramp up after the 1970s. Okay, the debate though is, has there been a more recent acceleration? And I hadn't thought about this all that serious because I thought it was already going fast enough. But I think it's interesting to take a peek. And so I've done that with a colleague. And I just think it's interesting. If you just look at it here, you probably can't tell in the room. But if you look at the orange data and the line through that, it's not as steep as the line, the red line going through the red data. So somewhere around 2015, 16, things took a jump. And it's hard to see here. I've looked at other data sets recently, and you don't see that in surface air temperature. Here's another way of looking at it. We're looking at a different data set now on the upper left. And that's a time series where you can sort of really see things. And it only goes back, I can't even read the darn thing. What does it go back to? Around the 1980s. It goes to 1980 out to the present, this year, right now. And you can see the 2006 warmest 7 got that on there. Those are the warmest 7 years in global history since we started a global thermometer record. So if you look at where on the other graph that we were looking at before, different data set, but plotted in a different way, you can sort of see what's going on in 2016. There was a big peak in surface air temperature. Oh, wait, the one on the left, I'm sorry, this is where I get to sea surface temperature. See, it's SST. This is the ocean surface temperature, which goes into global surface. Okay, so we're just looking at oceans there. Big peak in 2016 corresponds to a jump in the air temperatures around the globe. And then it plateaus. And you can't really see it in Zeke's plot, the one on the right, but you know, all those orange dots at the top of the orange colored data set are all sort of bunched right next to each other. And you can see that on the left because you were going along and then it peaked at 2016 and you reach a new plateau. Temperature stayed high after that. And now we're getting another bump like that. So we back in 2016 and started looking at this. Finally, 2 years later, published a paper led by an oceanographer. That's why we're switching over to ocean data. Shenzhen Yin, he's at University of Arizona where he used to be. And we were like, what's going on here? You know, other people already pointed out, this is what happens during El Niños. But this is an awfully big jump for an El Niño. And what's going on now? El Niño. We have the first strong El Niño since 2015-16. So the last time this happened, the whole Earth atmosphere, surface air temperature jumped up. And now it looks like it might be happening again. Lo and behold, what's going on there? So here's the missing piece of the puzzle, which fortunately came right out after John said, you know, what's going on here? I'd like to learn more. This was published by someone I know from Australia in Sydney, and a team of the sort of their top climate scientists. And they're looking at ocean temperature too. And they, for the first time I know of, and I'm sure in the IPCC, there are lots of examples where this has already been done, but not on this problem, not up to this present moment. What we're looking at here is going back to the 1960s. We're not looking at air temperature. We're not looking at sea surface temperature. We're looking at ocean heat content. Now, why is that important? When we trap heat in the atmosphere, you know, on the planet with greenhouse gases, thankfully, 90%, over 90% of that heat goes into the ocean. And if the oceans weren't taking up the heat, we'd be broiling. We'd be like Dubai everywhere. It would suck. Okay? So the oceans are doing this amazing job for us. And what John, you know, his student Lee and John did and all their colleagues is they didn't look at one data set. They looked at all the ocean heat content data sets. They wanted to get, you know, so you don't know, every data set has its uncertainties. The paradigm is that if you average them all together in an ensemble, you get the best estimate of what really happened or what will happen. So, you know, when you look at, you know, climate model projections, temperature, precipitation, or anything else, those are usually averages of like 20 or 30 models to get the best ensemble. We're starting to get to the point where we might be able to do better than that, but this is the best way for looking at data. And those boxes, those blue, you're seeing the ocean heat content in red, pretty clear it's going up. No surprise to anyone. But what he did that I thought was so remarkable is they then looked at the rate on decadal averages of ocean heat content increase. I wanted to point out here the units are pretty cool. These are 10 sextillion joules. That's a lot of joules. Sextillion. I had to look that up. Okay, so you can see there clearly those boxes are getting bigger. that means the ocean heat content is accelerating. What they did in this paper really that got it into a really top journal was they looked at why and where all this heat is going. And it's all going in near the surface and intermediate waters. And at the end of the paper, they say something that really is disquieting to me, because it's obviously increasing. They say, as the ocean warms, it will take up, and it's not just warming, it's becoming more fresh. It will take up, and therefore less mixing down, right? You have fresh water on top of salt water. The heat won't be able to penetrate the way it used to. So the ocean mechanism for taking up all the heat could be about to start reversing and getting less. But so far, it's been getting greater and greater and greater. So the point here of this whole story, this whole rant that I'm giving you, is that when you get an El Nino now, the ocean is so much more loaded with heat. El Ninos have always released heat from the Western Equatorial Pacific, but now they can release more and more heat. Okay, so I'm very much looking forward to, kind of in a scary way, what's going to happen over the next year. Because in 2015-16, you didn't get the big jump in temperature until after the El Nino had already been around for a while. We're actually started getting the big jump before the El Nino. And for sure, there's other parts of the world ocean that are giving off heat. Global SSTs, sea surface temperatures, remember, are also unprecedented, record-breaking hot. So it's like the whole ocean is like giving it up in a greater degree than ever before, okay? And we don't understand exactly what's going on. These guys sort of say, like, maybe a whole pile of grief, but I'm ready for them. Okay, we're good friends. The other thing I wanted to show you is you don't want to fight for renewable energy and the extinction of the fossil fuel era. Those are two things that we need real bad to solve this problem, just because climate change is getting worse. Okay, there's another element that Jim was thinking about. He didn't really express it that much in the paper, but I know the way he thinks. He sees the climate system as a non-linear system, meaning it's prone to jumps. It's prone to positive feedback, and shit happens that we don't fully understand. And so this was in the National Climate Assessment, and you might enjoy reading about it. Everyone has their different perspectives on tipping points. I was lucky to be working on tipping points way, way back. And so I've really tried to keep on top of it. But here's an example of a tipping point that I worry about. There are two types. One is a tipping point that causes an acceleration in climate change, or a nonlinear increase in warming. Okay, we might have just talked about one. We don't understand it yet. This graph mixes both of those up, and I've always hated that, but that's what the community likes to do. One of the examples, let's just look at the high latitude northern hemisphere, where it's really quite interesting. Big gray, loss of summer Antarctic ice. This is happening. It's been happening for some time. The Arctic loses a lot of sea ice in summer. It warms up, the sun's out. But now we're losing it. We're going to lose ice cover for months at a time in the Arctic. And what does that do? It makes the planet less reflective. So all of a sudden, heat that was just being solar radiation coming in, instead of being absorbed by the system and Earth system and heating up the atmosphere, it's just being reflected back to space. It helps keep the planet cool. But now that cooling mechanism is going bye-bye. So that is going to cause, and is causing, if you look at any map of global warming, where is it warming the most? In the Arctic. That's why. That's a tipping point. And the question is it accelerating? When will it go seasonally ice-free? And we used to say, and I've written papers on this too, you know, that it would happen maybe in 2030s, but it's gonna probably happen maybe before then. Another one, which is related, are the polar ice sheets. I don't like this graph for multiple reasons, because I think it doesn't mention the East Antarctic ice sheet is also falling apart, but the West Antarctic ice sheet certainly is, as is Greenland. Again, big white reflective spaces on the planet starting to fall apart. These, if we lose the ice, of course, we get massive sea level rise. It's going to take a while. These take centuries to millennia to lose ice sheets. But the point shifts. Again, I didn't write this report. I didn't get a chance to review it. I think they made a mistake. It's not the boreal or a big problem. It's the fact that boreal forest is burning down. And that causes a change in the planetary albedo as well, particularly in winter, because you don't have trees, you have soil and snow on it. But you're also releasing all that carbon, CO2 from the fires into the atmosphere, and black carbon, which are accelerating in a nonlinear fashion the forcing of climate system. And of course, all of us who breathe that damn smoke are going to suffer more as a result. And you don't know what it's, I mean, it was bad this year, but I've been out west for a long time, and it can get a lot worse. And I could go around and look at this map with you for as long as you wish, but there are these other positive feedbacks. The biggest one that I'm glad they put on here was the loss of stratocumulus cloud. And it's been speculated, we look at the paleoclimate record, go back, 50 million years, it was a lot hotter. And the question, how the hell do you get so hot? And one of the ideas is, well, we lost the stratocumulus clouds along the Eastern Pacific and Atlantic and other places. They are very reflective. They're at lower latitudes. You lose those clouds, all of a sudden the heat is going to be absorbed. A lot more heat's going to be absorbed and re-rated in the atmosphere. So there are a lot of these positive feedbacks, and we don't really understand the time-dependent dynamics of any of them. And there are other ones on here, like the loss of the Amazon or loss of global corals, which probably won't affect the global climate system all that much, although the Amazon maybe. And yet will have profound effects on our biodiversity and water supply in certain countries. Into the Amazon, South America, and natural wonder are being just destroyed. So what I'm hoping is that you take all away from this talk that climate change is getting worse. The impacts are getting worse too. And I think this is another thing that I don't like about a lot of my colleagues. And I'm not criticizing them, but I wish they would highlight, remember, it's not just the climate change, it's the suffering that we're causing around the planet, particularly in countries where they did nothing to cause this problem. They're along for the ride and they're getting screwed. And they're getting screwed because in a lot of places around the planet, climate dynamics just isn't good for them. But also, they don't have the money to be resilient. But it isn't too late to save the day. That's the good news here. And I would just like to sort of clap for you guys because you're helping to save it. Okay, but that doesn't mean we can sit back and say, okay, Michigan has these wonderful laws now, all is well, because we know the laws aren't good enough. And we also know they're entirely vulnerable. All right, we have to make these laws durable and we have to make them stronger. So thank you all. Hopefully, if we do this right, I've heard this already in this morning, Michigan becomes a national leader in saving the planet. And that doesn't just mean we can all get a nicer cloud in heaven. It means the economy of Michigan will be outrageous again, but it'll be a clean and just economy.
Questions?
Yeah, I'm happy to take questions. We always start over here, but I'm gonna start with you because you're a rabble rouser. I know.
Thank you for being here. My next door neighbor believes that climate change is natural and humans have nothing to do with it. Though we have some discussions about that from time to time.
You're not alone.
But here's what he asked that stumps me, and I'm hoping you can help me. Hundreds of millions of years ago, we had similar levels of CO2 in the air, higher levels, actual higher temperatures, and somehow on a 400,000 year cycle, temperatures went back down again. How did that happen? I don't know.
Well, there's some actually clues there. One thing is point out is whenever CO2 is higher, no matter the cause, it's warmer. I'm a paleoclimatologist. I led the first IPCC chapter on paleo. And that was one of those things we went after hard because we're sick and tired as much as you are. So whenever CO2 is higher in the atmosphere, it appears that it's been warmer. Whenever it's lower, it's been colder. Often, glaciers are associated with low CO2 and things like that, glacial periods. What's controlling things on timescales longer than 400,000 years are geological processes. For example, the amount of production of CO2, which is very slow naturally via volcanic activity. But it's not just volcanoes that you see, it's volcanoes under the ocean. Because, we have plate tectonics and you've probably all seen the rings of fire and ocean spreading, what's going on in Iceland right now. The mid-ocean ridge is opening up under their airport. That is when CO2 gets emitted, but it's very slow, it accumulates very slow. And that's balanced by the erosion of rocks. And there are a lot of things that control the erosion of rocks. How high are the mountains? Are they in wet regions or dry regions? Things like that. But people have studied this, believe it or not, and they found that you can explain the big shifts in CO2 on the long time scales with the playing of these two variables, the production volcanically, and so the rates of ocean spreading, the rates of subduction, the rates of mountain building, all these rates change in time. And if you figure out the mass balance, in terms of how much CO2 should be emitted versus how much it's taken up by weathering, you can explain the long time scale patterns. But once you start getting into the 400,000 year range, you're starting to get into the astronomical theory of the ice ages. And what's going on this works on all time scales, but it gets to peak, and it seems to be more the last million years or 2 million years. There is a 400,000 year cycle. There's a much stronger 100,000 year cycle, much stronger. And there's also 41, 23, and there's some other ones that are smaller. Okay, these things are crystal clear in the paleo record, have been studied for a long time. One of my advisors was the person who figured all this out, John Embry, the pacemakers of the ice ages. And what's going on there are geochemical processes in the climate system. So we can model the climate system in terms of the atmosphere and the oceans. We can model it in terms of the ice. We can also model it in terms of the flows of chemicals in the atmosphere and in a natural setting. It gets a little harder once humans start screwing with it all. But the point is that part of this, we always have lower CO2 during glacial periods. And that relates to the fact it's colder, the ocean can absorb more CO2. The Southern Ocean tends to be, the winds are stronger, so there's a lot more biological productivity. And that biological productivity sucks up a lot more CO2. In other words, the climate feedback that is drawing down the CO2 naturally. And the change is small compared to what we're doing now. It's like 30%. Now we're doubling it. And we're going in the opposite direction, which no one could figure out. And we wrote about this in the IPCC. There is no one that's come up with a mechanistic model for how you could possibly get what's going on now without fossil fuels. And you also can see it geochemically. This is clearly not a natural phenomenon. But anyhow, I could go on and on. I hope that helps a little with your crazy neighbor. Yes. No, we'll come back.
I just read Michael Mann's new book, Our Fragile Moment. And the one takeaway that's optimistic, and I just want to get your feedback from that. Yeah, there you go, feedback, is he seems to be that if we do achieve this, net carbon neutrality, that the reduction going back, in terms of CO2 dropping off is actually going to be faster than what had previously been feared. Any comment on that?
Yeah, I haven't read his book. It's hard for me to read climate science books. Because I just don't sleep at night. But that is a change in paradigm. In other words, we were saying for quite a long time, we being the scientific community, is that the climate system is a sluggish, think of it as a big ship or something. You can't turn around in a dime. And so once we stopped putting more greenhouse gases in the atmosphere, it would continue to warm. I think what Jim Hansen is saying, don't be so sure that it isn't. And Mike is like, he wrote a very, I thought, thoughtful piece. I don't know where he wrote it, but it's like on the web, sort of going after Jim. And it was very fine. There wasn't aminosity or anything cloaked in the whole thing. But I don't know who's right, but I really suspect that Jim Hansen's right. But we don't know. The uncertainty is large. But what's going to happen when we stop CO2 going up in the atmosphere? The problem is a lot of the CO2 stays in the atmosphere for as much as 1 million years. So it's going to, as long as it's up there, it's going to keep warming. And as it starts to cool, the atmosphere starts to cool, the oceans are the reason I wanted to talk about ocean heat content. Will just give up more heat because it's trying to stay in equilibrium with the atmosphere. So I think a safer place to be on what's going to happen when we reduce the greenhouse gas emissions to zero is that'll be our new climate. And that'll be the new temperature of the planet. That'll be the new normal. Finally, we'll have a new normal that we can actually. Right now, the new normal is it's changing. And we'll have all the climate extremes that we're getting at that stage. The same frequency, the same severity, and the same duration. In other words, we let it get really hot, we're going to be in a really costly planet, I think, both in terms of human lives and economics. And that's more important than trying to debate this. Is it going to get warmer or is it going to get cooler? You can bet on it, it's going to stay about the same. But I think, Jim, what Mike is missing are these tipping points. That's why I threw that in at the end. These tipping points could really continue they're slow. The ice ages, they take forever to come into equilibrium with the climate system. If we lose a big part of the Antarctic ice sheet, that's how we were so warm during the Pliocene 3 million years ago. You need to have that big positive feedback of the planet becoming less white. And I can't see why Mike can assume that won't be a threat. I think what he's saying is we're going to stop it before then. And he might be right, but we don't know. We don't know where we don't know where these tipping points are. And some of them, in the Northern Hemisphere example, I think it's surprising everyone scientifically how fast they're already starting to come. I didn't even mention the permafrost. We melt all the permafrost. It's loaded with carbon. And it's quite possible we won't be able to stop. So Mike could be right, it's when emissions stop going up. But we might not be able to get to net zero because the natural system will keep pumping added CO2 in the atmosphere because of what we've done with the warming. And that's one of the reasons why University of Michigan has a big initiative into terrestrial natural climate solutions. It's not going to be agriculture, it's going to be forests, maybe grasslands. And we're putting a lot of effort into figuring that out. Yes.
Here's my alarm. You want to turn this on?
So you alarmed us with all this heat that's in the ocean. But for a long time, we've had all these models that predict weather, and they've got to have thermal transport aspects between water and the air. did those models miss radically that transport that's going on between the air and the water?
No, I think on a planetary average, probably not so bad. But I'm not an expert in that coupled air-sea interaction modeling. It's pretty far from what I do. But my sense is that they didn't get the details. So when we get a paper like I just showed you here, published in October, the whole modeling community is like, the first thing they went back to is their models. Do we get this? Because what they were able to do for the first time, not just get a time series like we looked at, but they were able to show where the heat is accumulating and where it's not. And are the models capable of getting that perfect? No way. You know, but as a result of empirical data, they will be able to improve. They'll be able, the understanding will improve in the processes, and the next generation of models will be better. Models are incredibly good at many things now. They're not perfect at a lot. So for example, I worked a lot on mega drought. It's an in thing in the Southwest because we're in a mega drought. And we found, and it's created a nice amount of controversy, that the models cannot simulate mega drought. A few community colleagues are saying, yes, they do. But they're not simulating mega drought. They're really underestimating mega drought. And so we're going to probably have more mega drought. Let's go to the back of the room. We'll go over here because she's a C-suite. You can pick either one.
She got one from the ladder.
Uh-oh, is that me?
Yeah. I'll just use my big voice. I do a lot of work, think more about demographics in a lot of areas in policy where I think economics and other policies are not taking into account demographics of the world, i.e. that by 2050, even though I see climate and all kinds of economic projections going into 2080 or 20, you know, in the next 100 years. And whenever I ask, and does your model think about the fact that the world's population will start shrinking, which has never happened pretty much in human history. And I'm curious about climate modeling. Does it take into account the idea that we are, and in fact, if we see population spirals as they're demographically kind of lined up, do the models look at that for like from 2050 on? What does it mean that we're going to actually have fewer people on the planet instead of growing?
So we're talking about demographics and what the trends are, and the population growth is really reversing. I mean, we're still, you know, where are we now? We're going to still get up to 9 or 10 billion, people think. But we were not talking 13 anymore, you know? 10 years ago, we were talking like bigger numbers, 11, 20 years ago, we were talking 13.
They were pretty crappy numbers from my study of demographics. Like, why are they talking about that?
Yeah, and the climate models don't do anything to do with it, have nothing to do with the demographics. In other words, one of the things we have to do when we project climate, where's the biggest uncertainty? It's what people are going to do. We don't know how many people there'll be. We don't know whether they'll actually be all like you and doing the right stuff, or they're all going to be like doing what Exxon wants them to do and DTE and still pumping gas and stuff like that. So it's not part of the climate model. You know, it's what we do is we take scenarios in terms of emission of different greenhouse gases, and we now are pretty sophisticated in connecting those scenarios to sort of real life. Think of it as futures, you know, like if you read a history book, these are plausible futures. We get multiple plausible futures, but ultimately they end up emitting a certain amount of heat warming, you know, of warming greenhouse gas. And we can certainly play games and look at, you know, methane versus CO2 and that kind of stuff. So short-lived versus long-lived greenhouse gases. But we have to have those scenarios. And I don't know if that answers your question, but there's no demography in these models. And she was next, I think. Just to be fair.
Yeah.
Support.
Okay, Yeah, so with your experience on both the IPCC and the PCCN, I was just curious if you think the carbon neutrality commitments of the University of Michigan and now the state of Michigan are aggressive enough for the science that you just talked about?
I don't know if you can tell from my talk. Right, I mean, it's like, no, they're not aggressive. But I'm pretty happy to be here. I arrived back in Michigan. I grew up here, but I went away for a whole pile of decades. And I would come back every year, you know, once to get married, but every summer I'd be back. And my wife was born in the university hospital. It's so cute. I'm sure she was a cute baby. But the point is, I'm really proud to be here. I'm really proud to be at the University of Michigan. I'm really happy for people like John and a whole bunch of other Ann Arborites and who've just kept the pressure on University of Michigan. In that time, it was Mark Sissel, our president, to sort of make the big, it's a huge commitment. We estimated in the PCCN, it'd be like our geothermal deployment would be, you know, $2 to $3 billion. And you're a president who's making a decision that's gonna perhaps hamstring all future presidents. And I'm a dean, and I know that's gonna hamstring me. But you know, it's the right thing to do. And since he's left, we have a new president who cares a hell of a lot more about climate change. And we are decarbonizing our endowment. We're going way beyond the PCCN. And I think at the same time, there are things like the Michigan legislation coming online, which will make it easier and less expensive for the University of Michigan to do what they want to do. And listening to the governor a couple days ago downtown, you know, she's right. We're the best in the Midwest. We're one of the top 5 states in the nation now. If we can maintain and get a durable, this is a durable solution. So we should be damn proud that we are ahead of almost every other state in the country. And why do I care about that? I want to see climate change stop. But I think if Michigan and a couple other Great Lakes industrial states can be leaders, then the rest of the country will start to say, huh, it's not just those really progressive states on the, I know she's from California, you know, the Pacific or Atlantic coast. It's the heartland, it's those purple states, even some red states, look what Texas is doing. You know, all of a sudden the costs will start to really make it clear that this energy world is much better for people, pollution-wise, pocketbook-wise, climate-wise, than fossil fuel world. And I want to be, that's another tipping point, right? We talked about tipping points. That could give rise to a nonlinear change. It's going to keep speeding up as it becomes economically the way to go. So I'm pretty happy. You know, happier than I thought I would be when I arrived.
One more question.
You gotta pick it though, John, because I don't want to make any comments.
You focused on CO2. You focused on CO2.
Wait, John, get the mic.
We got 2 more questions, one here and then one here.
Okay.
Right, that's the kind of employee I like. Tell the boss. No.
Can you hear me now? You focused on CO2 in relation to climate warming and so forth, but what about other things like methane? Is methane important? Should it be controlled more? Is that not also causing global warming?
Absolutely, methane. There have been some good things to come out of COP so far. The thing in Dubai. One of them is that the major petroleum exporting group in the Middle East, I guess, with quite a 50% of the big companies in the oil patch are all agreeing voluntarily, so we'll see what happens, to curb methane emissions. Methane is incredibly important. One of the reasons we got to get out of natural gas really fast is natural gas is methane. And methane production at the wellhead all the way to our house is leaking out of the frickin' pipes. And it's going into the atmosphere, and it's a much more potent, although shorter lived, greenhouse gas. So one of the reasons natural gas absolutely is public enemy #1 now, behind coal, is because of this leakage of methane. We better get rid of our natural gas. And that's why I'm saying, you know, and you listen, what has the Pope told the COP? The Pope has said the most logical, scientifically credible thing so far of anyone at the COP. And I'm not Catholic or anything like that. I'm just saying, the guy knows what he's talking about. And he says, what we're after as a human race who cares about the planet is phasing out of all fossil.
Okay, Pat. There's something in the middle of the room. So here's what I'm curious about. Intuitively, I've sort of sensed that we've undercalled it, we're hitting these tipping points. Is there any research happening yet? Let's assume we're successful. I need to. I have to assume we're going to be successful, and everything you just said about Michigan, state, university. Project forward, let's assume success. Is there any research going on about the recovery capacity of our ecosystems and the pace of that capability? You know what I'm getting at?
Yeah. So the thing I worry the most about is biodiversity. Once it's lost, it's lost. So I'm worried that we're going to lose biodiversity. But I can tell you one of the reasons, I already gave you a clue. We're working on natural climate solutions. We already heard from another speaker that we're working on technological climate solutions, taking CO2 out of the atmosphere, using it for things. We're trying really hard as a community. It's not just in Michigan, although we're one of the world's leaders in this. We're trying really hard to figure out how to bring the CO2 levels back down, because we don't want to just sit around debating it, what Mike says versus what another scientist says. What we want to do is ensure that it doesn't happen. And there's big error bars in all this stuff. And I have great faith. I've studied not only climate change over millennia in the past, but also ecosystem change, terrestrial ecosystem change. And I'm married to a person who does the same thing in the ocean. And so I feel like ecosystems can respond. No matter what we do, there will always be ecosystems. But it'll be a mass extinction if we just let things go too far. So what we're going to do is get ready, not just to reduce the emissions to zero, but to let's suck the CO2 out of the atmosphere and put it away. And I do not believe the DTE, the consumer, is going to develop a carbon capture sequestration effort that is going to be cost effective. No, we've been trying to do this for 30 years. We haven't even figured it out. It's very expensive compared to just building renewable energy and batteries and things. But on the other hand, we might have to do that for other reasons. And therefore, I guess some of my colleagues would say it's good that we encourage the oil patches waste some of their money on it, because we are going to need it. Thank you. Yeah, sure.
You mentioned volcanoes and you were talking about millions of years ago where they added a lot of CO2 to the atmosphere. And I just wanted the audience to know that now they cause cooling. And I did a plot of each time when the temperature had actually dipped, and it can correlate to a big volcano going off. And Krakatoa, in
1870, no, 1870.
the 1912, which was the largest one in the 20th century, now the rooftop had the biggest dip. So I thought it was really interesting to see that it dipped.
Two completely different things. Another great thing that Jim Hansen did once, when he go to Congress before anyone else would talk about this stuff being real. And they're like, your models can't do that. You can't predict anything. Then Pinatubo erupted. I remember that. 93, I think it was. And he immediately took his climate model, which is actually one of the poorer ones. I used to use it too. And he simulated what will happen over the next 2 years. And then he wrote a paper 2 years later and said, look how good we got. Volcanoes, when they go off now, they cool. So when you've heard about solar engineering, the idea is to create artificial volcanoes. Put a lot of aerosol in the stratosphere. What could go wrong? And it's absolutely crazy. I mean, Mike and I are on the same page on this one for sure. And, but what we're talking about in the longer time scales is this, and so if you had a plot like yours, time versus volcano versus CO2, you would see no CO2 blip with any of the eruptions we've had. Yeah, we have super precise to the, million parts per million resolution of CO2 in the atmosphere. You can't see any effect of a single eruption. But when you have a million years of a slightly more eruptions, it adds up. And I think that's the interesting thing. And of course, think of rock weather. That's worse than watching grass grow. It's like slow, but over millions of years, it gets the job done. Yeah.
Okay, round of applause.